Okay, let's go back and remind ourselves about rates of change. And this first screen is actually just a lot of writing, literally reminding ourselves of what we know about rate of change. So we had looked at two rates of change. What were they? And just to suggest, I'm going to ask a lot of questions on this first screen, and you may just want to press pause after I ask the question, think about it, and then see if you got the right answer. So we had two rates of change. First one was an average rate of change. And what did it measure, or how did we measure an average rate of change? And that was where we took 2 points on the curve and connected them, because we need 2 points to calculate slope, rate of change. And that was called a secant line. And that gave us, what was going on between those 2 points. It in no way matched the actual curve, but just looking at those 2 points, we could get an idea of what's happening. So that was the one type, average rate of change, slope of a secant line, 2 points on the curve. And the other rate of change we did, that was the instantaneous rate of change. And that's where we only had 1 point, and we called that then a tangent line. Now, the problem was, we can't do slope with only 1 point based on our grade 9 and 10 slope skills. And so what we did was we approximated it by using a second point that was really close to the one we wanted. And then we had 2 points. Now, we're technically still finding the slope of a secant, but because those 2 points are so close together, it's almost the slope of the tangent line. And that's why it's an approximate every time we do the IRC. So how did we do that? What was the formula? So if we want to find the average rate of change on a closed interval from A to B, then what was the formula? Now, we used x1 and x2, but that formula was f of x1 minus f of x2, sorry, other way around, f of x2 minus f of x1 all over x2 minus x1. Basically our basic slope, rise over run. Rise went with the y values, f of, run went with the x values, the a and the b. So that one's pretty straightforward, I hope. What did we do differently for the instantaneous rate of change? Well, remember there, we went with 2 points still, but the one was really close to the one we wanted. So if we wanted the instantaneous rate of change at x equals a, that's this guy right here, then we went for another point really close to it where we added to the x value, and that affected what went on in here, and we wanted that amount to be less than or equal to 0.001. Well, if we put that into the formula instead of h, like we literally put in the 0.001, take a look at what happens to the denominator. We get a plus 0.001 minus a, and that all simplifies to f of a plus 0.001 minus f of a all over 0.001. Now, if that makes sense to you, use it. If you want to do it the way we did in the first unit, it works out to the same thing, go ahead. But essentially, that's a simplified version for the instantaneous rate of change calculation. All right, let's take a look at using those formulas then on this cubic function, negative 2x cubed plus 8x. And first of all, finding the average rate of change on a closed interval, then another average rate of change, and then an approximate instantaneous rate of change. Again, if you're feeling confident, press pause, do the calculations on your own, then come back and look at what I've done. But if it's been a while and you didn't really enjoy this in the first unit, just listen in as I work through it. So for the first one, tell me that you're calculating an average rate of change, and it's going to be f of 4 minus f of 2 all over 4 minus 2. And that bottom's easy. It's going to simplify to 2. On the top, though, we have to do some work, and whether you grab a calculator and substitute f of 4, use your brain because it's not that bad, but the numerical value for the first one, f of 4, is negative 96, then we're subtracting. Well, let's substitute 2 into the function, do the math there, and we get a 0. And that should mean something to you, the fact that we got an answer of 0. Put it all together, negative 96, take away 0, and then divide by 2, and we get a numerical answer of negative 48. In a minute, we're going to talk about what that answer means visually. Second one, average rate of change on a different closed interval from negative 1 to 1. So it's f of 1, take away f of negative 1, all over 1 subtract negative 1. Watch your sign work there, your integer work, so that comes out at a 2. Again, substituting the value of 1 into the function, we get an answer of 6, and then we're subtracting. F of negative 1 is negative 6, so we've got to put that in brackets to separate the signs. The top simplifies to 12, 12 divided by 2, and we get a rate of change of 6. Again, think about what that means visually. We're going to tie that in. Now for the instantaneous rate of change, again, we're approximating it. So we wanted to do that at -2, but instead we used, a second point nearby, -2 plus 0.001, and subtract f of -2 all over. And when I put those two together, -2 plus 0.001, subtract -2, I get to 0.001. So we're really finding f of -1.999, which I'm so not doing in my head, or even close to that. And because I'm going to use a calculator to work through it, I'm just going to do it all at once. And I simplify the top, and I divide by 0.001, and we get to -15.988, and then it kind of keeps going after that. So we're approximately equal to -16. Okay, so that's nice. Let's scroll a little bit, try and leave those on screen, and let's interpret these results as to how it pertains to the function itself. So let's get a sketch of that function. Again, that's a nice little recap skill, so if you want to do it on your own and then check with me, go for it. Otherwise, listen in as I work through. Just checking how much space I have. Okay, so if we want to sketch this, factored form would be really nice. So our original function, -2x cubed plus 8x. Remember to go for the simple factoring types first. The common factor, -2x, leaving x squared minus 4. Awesome, difference of squares, x plus 2x minus 2. So that's giving us information about the zeros. And just on a rough sketch then, we know that there's a 0 at 0. Let's try that one, a 0 at 0. Yeah, we're back. 0 at 0, a 0 at -2, a 0 at +2. This is a negative cubic, so it's going down left to right. So it's looking something like that. So now let's look at those answers. If we look at the answer of -48, and that was on the interval from 2 to 4. Well, we can see the intercept of 2. We can't see where the 4 is. It's down there somewhere. But what does that answer of the average rate of change of -48 mean? It means that in that section, we've got a fairly steep negative slope going on. And if you think about that, yeah, that kind of makes sense. The answer of 6, and that was on the closed interval from -1 to +1, says that, well, that's, roughly here to here, and even though it's a curve, if I connect those points, I'm looking at a slope that's going up left to right, a positive slope. Yeah, I feel good about that. Last one, instantaneous rate of change at x equals -2. Says that at that point, if I just skim along it, and that's kind of hard, because I got a really thick pen, it's got a slope of -16. Yeah, it's going down left to right. So understand that the rate of change stuff tied into slope gives us information about shape of the curve as well. Because if on an interval my slope is positive, like in the green section, the curve's going up left to right. If on an interval my slope is negative, like in the red section, or instantaneously in the black section, then the curve's going down left to right. And really that's what this next part is saying. In general, what would it mean if the average rate of change or the instantaneous rate of change is positive? Well, then the function, short form, is increasing on that interval. And if the average rate of change or the instantaneous rate of change is negative, then the function is decreasing on that interval. And then the interesting one, because we didn't have this example, what if the instantaneous rate of change is 0? Well, remember that rate of change slope. So what does it mean if the slope is 0? Well, lines which have a slope of 0 are horizontal. And if I draw a horizontal tangent line, where would that happen? And it would have to happen at a turning point. if I've got this curve, even if we just stick with a parabola, and my tangent line is horizontal, that's happening at the vertex. Notice that in part C, I didn't say that the average rate of change was 0. Why not? Does the average rate of change of 0 mean anything? And I'm going to leave that one with you to ponder, and we'll talk about it together tomorrow. Homework's on page 235. Looks like a lot of questions, but they didn't run too badly. They have a couple of applications in there, real-world problems. And remember their rate of change. You know, we had the example the other day with the rock being thrown up into the air. Height in meters, time in seconds. Height compared to time, meters compared to seconds. You're getting a speed or a velocity, and I know they're different, so don't tell Hoba I just said that. Okay, so watch for those ones that are applications and make sure you're comfortable with those as well. Okay, good luck with that.